In this video, we will take a look at Unit 9, Day 1, an introduction to probability. If you were gone from class, this is a perfect opportunity for you to see the notes that we covered in class. We're going to be talking about probability in this unit, which we will define here. Probability is really just the likelihood, fancy word for chances, the likelihood of an event occurring. Okay, and what all that means is the chances of something happening. And probability is a mathematical formula that we use. It's a calculation. Okay, we would say it like this: P standing for probability, parentheses, event, meaning the probability of whatever event we're talking about. And we'll do an example or two in a little bit. But the probability of that happening is always the number of favorable outcomes, meaning the number of times our event that we're wanting to happen or checking to see, that event, how many times that occurs, divided by the number of total outcomes. Okay, and that's how we find probability. Now, we do have this other concept of what we call the complement of a probability, or the probability of a complement of an event, which is really just a fancy way of saying the probability of that event not happening. And since probabilities always have to be between 0 and 1, you can't have a probability greater than 1 or 100%. You can't have a probability less than 0. Since that is the case, the complement probability, or probability of that not happening, is always 1 minus the probability that that event does happen. Okay, so let's talk about that a little bit more. We just said that in probabilities, okay, in probabilities, all right, probability always has to be between 0 and 1. Because anything less than 0% chance, if I wrote these as percentages, would be impossible. That couldn't happen. But it could be 0% chance that it happens, which means the event itself is an impossibility. It won't ever happen. But you just can't get a negative, those would be less than 0, a negative probability. They don't exist. For the same reason, we can't have anything that is more than 1 or 100%, if I wrote it as a percentage, likely to happen. That means the chances of something happening always at greatest would have to be 100%, which means it's guaranteed. So probability is always a decimal, fraction, or percent. Let me write that for you. Fractions, decimals, or percent that is between 0 and 1. So now we're going to take a look at whether or not certain given numbers could in fact actually be the results of a probability. Could these exist? Are they valid or not? And we're just going to write valid or not valid. If they're not valid, we're going to justify that by just explaining that it's either less than 0 or more than 1. It doesn't fit in that range. So the first one, 0.452, that would be like 45.2% if I wrote it as a percentage. Well, that's entirely possible. That could happen. So this is a valid probability. Okay, number 2, 4 out of 23. That could happen. We could have 4 chances out of 23 possibilities. That would be valid. But this one, negative 0.13, is not valid, because that negative number is less than 0. That's our reasoning, or our justification. Number 4, this is a probability of 1. Remember, that equals 100%. That is valid because that just means it's guaranteed. I did not spell that right at all, but you get the idea. Okay, got my R and my A switched, or R and U. That's okay, don't worry about that. You know what I mean. All right, number 5. 2.30. All right, that is not possible. That's not valid at all because this 2.3 is greater than 1. That's not a valid probability. Probability of 0, though, is valid because 0 means that's impossible, but it is a valid probability. It just means the event will never occur. And lastly, 34 out of 31, again, is not valid because that is there's not 34 possible outcomes. There's only 31, so you can't have more than what are possible. Again, that fraction is greater than 1, which makes it not valid. Okay? So as we move forward in our examples, we're going to be actually basing some calculations on the complements of these events. So in this first example, they tell you the probability school will be canceled tomorrow is 0.03. Well, that's actually fairly accurate considering we just had snow on Sunday, and it's April, that was April 14th. But this is kind of a made-up number for us. If the probability that school is canceled is 0.03, what's the probability that we will have school? Well, that's just the complement. That's like saying, what is the probability of school not being canceled? And what that tells me then, probability that it's not canceled, means I take my 100% total and I subtract the 0.03 probability that that is canceled, which gives me a decimal of 0.97, or I could write it as 97%. Either answer is okay. For our next example, they tell you the probability that Jessica goes to Florida this summer is 0.67. So what is the probability she doesn't go to Florida? Again, I would write that as probability of not going to Florida, or not Florida, which is again just 1 minus the probability that she does go to Florida, which is given to us. And that's kind of how we would write that, all right? And so I added a little extra work there. That's just 1 minus 0.67, which gives me a total of 0.33. Okay, and finally, in this example, we're told there are 12 red marbles in a jar of 50. So now they don't just give me a probability right away, they give me a more general scenario. So we got 12 red marbles in a jar of 50 total marbles. Okay, so when we are choosing a marble at random, what's the probability that you do not choose a red one? But then they also want the probability that you do choose a red one. Well, let's do this one first. The probability of not red is the complement of choosing red. So that'd be like 1 minus the probability that we do choose red. And if I set it up this way, that's actually going to help me answer the second question as well. So that's going to be 1 minus the probability of choosing a red. The number of favorable outcomes would be 12. And the total number of outcomes would be this 50. Well, we can also think of it like this. If there are 12 red marbles in a jar of 50 marbles, that leaves a total of 38 marbles that are not red out of the 50. Because to rewrite this in a subtractable fraction, that'd be 50 marbles out of 50. 50 over 50 is 1. 50 minus 12 is 38. Now, I don't want to leave my answer this way, mainly because it's not a simplified or reduced fraction. I would need to divide this out to make it more simple, or I could just divide it out and write it as a decimal, which I will do, which gives me 0.76. So that's the answer to the first question. But the answer to the second question we've already shown right there. The answer to the second question is the probability of choosing a red. Okay, probability of choosing red was 12 out of 50. And when I divide that out to its decimal form, that's 0.24. Okay, remember that these two probabilities, choosing red and not choosing red, should add up to a total of 1. 0.24 plus 0.76 does equal 1. And now we're going to move on to our next concept, and we're going to talk about what sample space means. You may have heard this term used before, but we're going to define sample space as really just the set of all possible event choices. All right? And so when we talk about these choices or selections, we're really just talking about all the possibilities in either a single selection or multiple selections. And we are going to use something called a tree diagram to help us map this out, where every branch, or actually every level of branches of this tree, gives us our selection or our options for each selection. Okay, so in this first example, here's what we have. We're going to write out the sample space of the genders for a couple that has 3 children. Now, we're going to take a look at each of these 3 children, and the order is important. Okay, so as these children are born, in their firstborn child, they really have 2 options. Either it's born boy or born a girl. Then, after that, their second child has the same 2 options. Third child has the same 2 options. But like, for example, if they had a boy, then a girl, and then another boy, that's not the same as a boy, and then a girl. Okay, because the birth order matters. These are 2 distinct possible combinations. They're not the same. So what we're going to do is we are going to make a tree diagram, and you're going to want to give yourself plenty of space to map this out. We're going to kind of start in the middle here. Every level of branches, we're going to go from left to right instead of top to bottom. Every level of branches is our first set of options. So in this case, our first level is our first child, which would be either a boy or a girl. From that, we are going to branch out to our second child. If they have a boy first, they could have a boy second or a girl second. But also, if they have a girl first, they could have a boy second or a girl second. But from there, we have another level of branches. Each of these branches out into our third set of options, which would be, if they have a boy, then a boy, they could have another boy, or they could have a girl. If they had a boy, then a girl, then they could have another boy or a girl. And kind of same ideas here. And if we follow these possible paths of this tree diagram, we get all the possible outcomes. They could have boy, 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 or boy, boy, girl, or boy, girl, that's a G, boy, or boy, girl, girl, or girl, boy, boy, and so on and so forth. And we get that there are really a total of 8 different outcomes. When it asks you to write the sample space, though, this is your answer. Okay? And if you put the whole tree diagram, that's fine. That's really what I would like to see. But this list is the sample space. How big the sample space is would be 8. But to actually write out the sample space, I want this answer. Okay? And so we're going to skip over these. If you want to try these real quick, though, on your own, pause the video. Otherwise, I'm going to quickly show you this answer anyway. If we were talking about rolling a dice twice, okay, or a die, a single 6-sided number cube, if we roll it twice, here are our possible outcomes, and this is what this would look like. All right, if I rolled a dice 6 times, this level of branches, okay, this first level, I've kind of spaced out rather than going all the way top to bottom, I would have run out of room. But this 1, 2, 3, 4, 5, and 6 represents our options for our first roll. I could roll a 1 first, a 2 first, a 3 first, a 4 first, a 5 first, or a 6 first. Then every one of these other branches tells me that second, I could roll a 1 through a 6 for each of my possible first outcomes, which gives me a sample space size of 36 different outcomes. I could have 1, 1, 1, 2, 1, 3, so on and so forth, all the way down to like 6, 4, 6, then a 5, or 6, then a 6. This covers all of them because the order matters. This is going to be important to be able to do that with these questions. So we're going to skip over our other example there and move on to the back. So as we look at sample spaces, we actually have a special little counting rule or a principle here. We've called this in the past the fundamental counting principle, or we can just call it the counting rule. We're going to have a lot of rules in this unit about how to work with probabilities. But our counting rule basically just takes those situations where we have multiple levels of choices or selections to make and talks about how to easily find the number of possible outcomes without making a tree diagram. And that is this, okay? Our total sample space size, or our total number of possible outcomes for those multiple selections, is always the product of event choices. Okay, product means multiply. Okay, another way you'll see this written is this: total equals x1 times x2 times all the way out to x to the nth number of choices. Okay, we'll kind of write it out formula-wise like that. But that's all it means. We're going to multiply all of these together. So if we had a situation where there are 12 female students in a class and 17 male students in a class, how many combinations could the teacher make if she wanted to choose one male and one female? I don't need to map this all out. I can just simply take the 12 females times the 17 males. And that gives us a total of 204 different combinations. Okay? I could also take a look at this next problem, and you might have seen commercials on TV like this, or even if you've gone to even McDonald's, they've got their 2 for $5 menu where you can kind of mix and match these different selections. So let's say at a dinner you can choose a drink, an entree, and a dessert, and we have to choose one of each. And the cost is $6. This is unnecessary numbers. We don't need that. But we do need this. If there are 6 options for a drink, 4 options for entrees, and 3 different desserts, how many combinations for those, it says lunches, really should be dinners, could you order? Well, we're just going to take 6 times 4 times 3. And we get a total of 72 different combinations. Okay, same idea on this one, but at a much larger scale. So let's say that there are 450 sophomores, 402 juniors, and 462 seniors. These were accurate numbers at least a couple years ago for here at TVHS. And let's say the principal wanted to take a representative from each class. How many different ways could they choose? Well, I simply take 450 times 402 times 462. And we get a whopping 83,575,800 different combinations of one student from each grade level. So that kind of wraps up our initial lesson on probability, or our introduction to probability and the counting rule. Okay, being able to do this is going to be very useful in future lessons.